First of all, I'd like to acknowledge my colleagues in Hubertus Fischer's group in Bern, and also funding from the ERC and the Swiss National Science Foundation. And apologies to everybody who heard the Nobel Geesthacht this morning already. There's going to be a bit of repetition on the method, but then some new results too. The ocean is the largest heat reservoir in the entire climate system. Because of that and the fact that the coupled nature of the system, whenever there's a change in any part of the system, the ocean temperature should change. This is also reflected clearly in the current global warming. This plot shows change in total heat content in different parts of the climate system over the past 50 years. And you can see that most of the warming is going into the ocean and only a small fraction is taken up by the land, the ice, and the atmosphere. This seems to even be true at shorter time scales. So these plots show some 14,000 decadal trends in Earth system energy and surface temperature, as well as ocean heat content change in CMIP5 simulations. So in pre-industrial control simulations, decadal trends show that any change in Earth system energy is much better approximated by ocean heat content change than by surface temperature change. So if you want to study the response of the entire system to any sort of forcing, outside external forcing, then we really want to be looking at ocean temperature change and how ocean temperature changes, because it's the most representative measure of the heat budget at any point in time. All right, so then that brings up the question, how do we measure ocean temperature? Currently there's some 4,000 Argo floats profiling the ocean in high temporal and spatial resolution, but obviously we don't have anything like that going back in time. However, we can measure noble gases. So, and for the rest of this talk, I'm going to be focusing on xenon and krypton only, for a reason that I don't have time to explain. But you could do this with other gases. There's a reason, but yeah, sorry. So the idea behind the concept of the noble gas thermometry is that the total amount of xenon and krypton in the ocean atmosphere are conserved. So however much is in the atmosphere is depending on how much is dissolved in the ocean. And the dissolution in the ocean or in any fluid is shown of noble gases, and really of any gases is shown in this plot. So with decreasing temperature, solubility increases. But not only does solubility increase, also the ratio between xenon and krypton solubilities changes. So to illustrate this, again, we have a plot here, a sketch of a colder ocean and a warmer ocean. And in the warmer ocean, not only is there less gas dissolved in the water, also the ratio of xenon to krypton dissolved is different from the cold case. This then is directly reflected in the atmosphere by an opposite change in the xenon-krypton ratio. So if you can measure the xenon-krypton ratio in the atmosphere, we have the amount or the ratio of xenon-krypton in the atmosphere is a direct proxy for the integrated global ocean temperature. So then, as you all know, we have samples of ancient air trapped in ice cores, which the idea is then to use those to reconstruct noble or ocean temperature via this proxy. And to give you an idea about the numbers we're looking at here, a global mean ocean temperature change of about 3 degrees, which is what we expect for a glacial interglacial change, is equivalent to a roughly 3 per mil change, or 3 per mil increase in the xenon-krypton ratio in the atmosphere. So this is well within what we can measure. However, gases in ice bubbles in ice cores are not a perfect representation of the past atmosphere. Before the ice is trapped in bubbles at the bottom of the firn, it has to go through the firn column where it is fractionated. The fractionation is mostly, or the dominant term of the fractionation is this gravitational enrichment that enriches heavier molecules compared to lighter molecules, shown here by the enrichment of 15N, delta 15N of N2 through the firn column. So this enrichment is kind of approximated by this equation here, depends on the height of the firn column H, as well as the mass difference between the two molecules we are looking at. So for N15, this mass difference is only one mass unit, which leads to an enrichment of the ratio by 0.3 per mil. But for xenon krypton, this mass difference is almost 50. So this 0.3 per mil change gets scaled up to 15 to 20 per mil for the xenon krypton ratio, which is exactly what we see in the ice core data. So on the left here, I plotted the raw ratio, the raw xenon krypton ratio as we measured in the EDC ice core over the past 40,000 years. And you can see that the ratio is heavily enriched, like 15 to 20 per mil higher than the current atmosphere, which is 0 by definition. But we can measure the isotopes of xenon and krypton and to correct for this effect. So when we apply the correction, we get the corrected curve down here, which represents the reconstructed xenon krypton ratio in the past atmosphere. Right, then one more thing to consider is that there are other factors that influence xenon krypton, the partitioning of xenon krypton between the ocean and the atmosphere. So ocean volume, salinity, sea level pressure changes all have an effect, which we have to take into account to calibrate our thermometer. And this is done via a box model, and I'm happy to talk to this about this more later if anybody's interested in exactly in how this works. But yeah, so this is how we get from the noble gas ratios to the global mean ocean temperatures. Then on to the results. After doing the gravitational correction and our calibration, this is our reconstructed mean ocean temperature over the glacial and into the interglacial here. First, I want to highlight the temperature differences. In the LGM, our mean ocean temperature is roughly 2.6 degrees colder than present, whereas the early Holocene or the Holocene is slightly warmer than present. This is in good agreement with deep ocean temperature reconstructions. I'm showing here the Shanahan et al. Reconstruction from a recent paper that has the magnitude as well as the timing are in good agreement between those two records. And also bottom water changes reconstructed from other sites or from sites in the Atlantic and the Pacific all show a bottom water temperature change of 2 to 4 Kelvin, which is also consistent with our results. But so looking into a bit more detail of our record here, we can see that it's not a monotonic, the ocean temperature change does not monotonically increase. There's two steps, an early step during Heinrich 1, then almost a pause, and the second step into the Holocene. So this pattern is very reminiscent of any sort of southern hemisphere antarctic temperature change, as shown here by a compilation of antarctic temperatures by Pedro et al. In red, or a recent temperature reconstruction from the West Divide ice core site by Coffey et al. Or you could also plot CO2 or any southern hemisphere controlled or southern hemisphere temperature really. Which begs the question, is it the southern hemisphere that sets the temperature of the deep ocean in the southern ocean, which then gets transported throughout all the basins? Or is it the other way around? Is the temperature of the deep ocean set by other processes, which by then outcropping in the southern ocean sets the temperature of the southern hemisphere? So I think that's still very much an open question, like in which way this relationship goes. And finally, not only, it's also interesting to look at our new record with regards to circulation changes. By circulation changes, I mean especially the changes in the Atlantic overturning, meridional overturning circulation, as reconstructed by McManus et al. And shown here in orange on top. So it's clear that there's a bit of an antiphase relationship whenever the AMOC is in a reduced or off state, as during Heinrich 1 and to a slightly lesser degree during the Younger Dryas. We have the strong mean ocean temperature warming, whereas whenever during the Poling Alrod, when the AMOC is strong, ocean temperature doesn't increase or even decreases slightly. So this is a little puzzling if you consider how we usually think of how the deep ocean is or deep ocean temperature is set. with cold water from the south and warm water from the north, and now you're turning off the warm faucet in the north, but the mean ocean temperature goes up, which so that just doesn't quite add up at first glance. But what the AMOC does is it doesn't produce or take away any heat, right? It just shuffles it around. So maybe a more fruitful framework to look at this has been suggested by Eric Galbraith in a recent paper, where he looks at radiation changes, planetary radiation changes associated with changes in the AMOC. So in their model, when they reduce the AMOC, the global surface air temperature decreases, mostly in the North Atlantic region, northern hemisphere, but it has a global signal, which then reduces the global or the outgoing long wave radiation by quite a bit. The associated with the cooling are increases in albedo, so which leads to a decrease in the absorbed shortwave radiation, but this decrease is not as big as the decrease in the outgoing long wave, which leads to a net positive radiative balance throughout for as long that stays for as long as the AMOC is reduced. So if you have a positive radiative balance, that heats the entire system, and most of the heat is then obviously going into the ocean again. So this framework with AMOC off and increasing ocean temperature is very much consistent with what we see in our record here. Okay, so just a quick recap. We reconstructed global mean ocean temperatures from noble gases in ice cores. The LGM was 2.6 degrees colder than present. There's a good correlation between our global mean ocean temperatures and southern hemisphere temperature proxies. And the strong warming with AMOC off or reduced highlights the importance of changes in the radiation budget. So I'll be happy to take your questions. Thank you.
2.6 Kelvin is a very exact number, and what's the uncertainty on your method, and how could you quantify that?
All right, so the uncertainty of any single data point is like 0.5 or 0.4 to 0.5 degrees, but since we have like a bunch of data points that all reflect the same climate in the Holocene and the LGM, I think this can be reduced quite a bit. I'm not confident to say a number right now, but there's going to be a number eventually. Yeah.
I'm not sure if you mentioned this or not, but is xenon and are these noble gases, are they well-mixed gases in the atmosphere? Because the basis of ice core records assumes that the gases are well-mixed.
Yes, they definitely are. And we measured also some Greenland records and other records from other ice cores in Antarctica, and they all give the same results for the last glacial maximum temperature and also the Holocene temperatures. So, but to your question, yes, the noble gases, they don't react with anything, and the turnover or the exchange with the ocean is slow enough that the mixing in the atmosphere is happening much quicker.
Two preliminary notes. First, this project or the work I'm doing was funded within PALMOD, the big German project, and secondly, the work's preliminary. So the idea, first I'll shortly say what I mean by analog method, then I'll talk about the assumptions I make, and then I'll show some preliminary results. So the idea to infer something about a set of data from its resemblance to another set of data isn't new. In meteorology, it basically dates back to the Second World War, when the US Air Forces tried to make forecasts by comparing the daily observations to the past set of observations and then forecast from this resemblance. So in paleoclimatology, we have our puzzle pieces or our proxies. We have our pool of simulation data. And we then want to find those fields which are most resembling our puzzle pieces. For this talk, these are the proxies I use. They are selected from the Marquardt collection. They are mostly Alkanones, but there is other stuff as well. So not mostly, but half are Alkanone data. A question is, what do they represent? For simplicity's sake, I assume they all represent surface temperature. The simulations I use stem from a variety of projects and a variety of simulations. All are remapped to an 0.5 by 0.5 degree grid, and I use the nearest grid point to compare to the proxies. That was one too much. In our simulations, not only the fields are they are not only spatially complete, but they are also temporally complete, while our proxies are irregular, are sparse, and uncertain. So for this case, I have 2,100 about unique dates. I make my reconstruction for these dates and assume that I have the proxies for this date when the uncertainties of the individual samples overlap with this date. But what do the proxies represent? Are they snapshots? Are they averages? What kind of averages are they? Represent they centennial means, multi-decadal means, or even millennial means? And it makes a difference whether I compare to 50-year means or 2,000-year means. That is, for this case, I compare to 101 year means. For simplicity's sake, it would be better to really include the time frame that are represented by each sample. So it would be a comparison between data for very different timescales. But for this case, I only use the 100-year means. Many people have thought about how to use the tuple of uncertain data and uncertain dating. I simply assume that both stem from a normal distribution, and then I can construct a confidence ellipse by fitting an ellipse to these two-dimensional normal distributions. Then I get this kind of uncertainty envelope for my proxies for each of the 20 puzzle pieces I previously had. There's also a question how to compare, on which units to compare the data sets. So we can do this on the proxy units. Then we have to transform our model data to the proxy units, or we assume the potentially previous calibration to temperature units. Here's one example where, from the Markov collection, both units coincide. And we see that the pool of or the library of our simulations fully captures a huge range of temperatures, and our proxy is a small part of that. However, if you construct a pseudo-proxy from the trace 21Ka simulation, there's no overlap. How to select analogs? Traditionally, or in recent years, it's often done by using those simulation fields which have a minimum distance to the proxies. So, for example, by using the Euclidean distance. That's one way to do it. Another way would be to use the full uncertainty envelope of the proxies, which are the gray bars in all these four columns, and then select those fields where our grid points values fall within this uncertainty envelope for all proxies we're considering. So this would be, in this case, only for this example of 4 proxies and 7 simulated dates, it would only be the most greenish one. And all others would not be valid analogs. What does one get if one uses these assumptions? One does not only get the 101 year mean, one also would get the time series, the local time series behind this 101 year mean. One would get the regional series behind this 101 year mean. And we get the 101 year mean here plotted for annual data. The dots are the proxy values. However, the comparison is a bit unfair or overly positive, whatever you want to see there, because the proxies have different seasonal attributions, and I plot the annual mean. So there seems to be some resemblance between at some locations. Okay. If you use the Euclidean distance approach, we could now just have a look at how these, for all the dates we have for one proxy, how the values at this location, the best values for this location look. In this case, I'd say it's okay-ish. It could be better, but it's not that bad. For this location, I'd say it's pretty bad. So that's the best analog values at this location for this proxy. If we now do the full method for a pseudo-proxy experiment, in this case for trace 21Ka simulation, we get something like this. So if you see the blue line, that's the 101-year running mean for the sector I use from the trace 21Ka simulation. The reddish would be the full and the 90% interval of the analogs. That is, they always include the mean, but otherwise they are pretty flat. And even the median or the mean, doesn't matter what you show, doesn't show any, more or less any variability. And there are even cases as about at 11K where we don't have any analogs. For this case, I had between, let's say, 0, for the case where it didn't give any analogs, and about 16,000 analogs in my pool. Assume according to a certain uncertainty interval. How does that look for a real case? These are for 2 different uncertainty envelopes, one above for 2 standard deviation uncertainties, or 2, and below for about 4. So for the top case, the method doesn't find any analogs very often. For the bottom row, we find up to 40,000 analogs in our pool, which isn't really helpful, I think. And the reconstructions look like one would expect from these numbers. For the small uncertainty interval, we don't have much reconstructed. It fades often. And at the bottom, we have basically a flat interval for much of the time. And at the end, it spreads overly out. So I'd say the method works kind of, but for the moment, the results are very unconstrained. I'd say there are 4 questions to my assumptions that I find, or to the methods that I find most important. One is my selection of proxies too naive? So should I have been more careful in selecting them? Second, is our pool of simulations big enough to use a small enough uncertainty assumption on the proxies? We certainly need less simulated years, a smaller pool that is, than if you wanted to forecast the weather. So it's probably not 10 to 30 years. Nevertheless, probably the pool is too small. There are 2 more bigger questions. Are our simulations even able to simulate these climates? I reserve judgment on that until the Palmer project has finished and we have our simulations and can compare that. And the other one is, are our proxies really representing what I assume in the beginning, or are they even, no, let's put it differently. They are certainly valid paleothermometers at their location, but are their interrelations also valid? And there that basically is my first point rephrased, but I'm doubtful about that. And that's it. Thank you.
Today I will show you something about the Adderley circulation extent and strength, spanning simulation from LGM to RCP 85. Let me see The Adler circulation mainly is responsible for the poleward transport of heat and angular momentum from tropics to extratropics. And we should care about changes, future changes in the Adler circulation, specifically because its widening has been related to projected drying of Mediterranean, Australia and California, and the polar shift and the mid-latitude storm tracks. It is also related to increasing of monsoonal, the projected increasing of monsoonal precipitation and narrowing of the equatorial belt. Just to introduce you to the theory that is one of the most recent about what are the drivers of the Adler circulation, I show you here a cartoon from Levin and Schneider 2015 in which the Adler circulation is related to macroturbulence in the extratropics. So when we have meridional temperature gradient from tropics and extratropics, eddies start to propagate upward and equatorward from a region of eddy momentum flux convergence to a region of eddy momentum flux divergence. So the Adler circulation mainly, the extent of the Adler circulation mainly can be thought as a region between eddy production and eddy dissipation here. So just to make an example of the mechanism itself, when we have less contrast between equator and extratropics, we have less eddies here. The Adler circulation is generally weaker, and we have an increase of tropopause height and a more stable condition in extratropics. And this is what mainly happened during La Nina episodes or also during global warming. On the other side, when we have strong meridional temperature contrasts, we have more eddies, so high baroclinic instabilities in mid-latitudes, and the Adler circulation will be stronger, and also it will be poleward will be equatorward contracted. The opposite happens when we have a weak meridional temperature contrast. Previous finding about changes in the Adler circulation with global warming assessed that in CMIP3 simulation with high emission scenario, the dominant mechanism that is leading these changes in the Adler circulation is the subtropical static stability change. While in the next phase of the CMIP5 RCP85 scenario, Seo et al. Robustly pointed out that the main mechanism behind Adler circulation changes is the reduction of meridional temperature gradient almost in both hemispheres. Here we are asking what is the main driver of Adler circulation changes, and to do it we use a wide range of simulated climate from LGM to RCP85 with different forcing. So we have from LGM to RCP85, we have an increasing of greenhouse gases concentration. We have also an experiment such as LGM in which we have a reduction, an increasing of ice sheet cover. And we have also included mid-Holocene because it's one of the most different experiments across our collection because the main forcing is orbital parameter changes. This kind of approach can help us to extract robust results on Adler circulation changes with climate change without focusing on just one scenario. So we can extract results that are scenario independent. We use a collection of 27 models for the PI control simulation used as a reference climate here, and for each experiment we have a different collection of simulation here. For Adderley circulation metrics, we computed the deltas. So for each experiment and each model, we have a delta with respect to its pre-industrial condition, like here. The Adderley circulation, of course, is studied by the meridional mass stream function. And we identify the extent as the zero crossing latitudes in both hemispheres, and the strength of the Adderley circulation defined as the stream function maximum. The predictors that we are used to identify changes in baroclinicity are near surface static stability between 20 and 40 latitudes in both hemispheres, and meridional temperature contrast is defined as the tropical temperature, near surface potential temperature between tropics and extratropics. We use also in following the scaling theory, we use also tropical tropopause height and we use tropical mean surface temperature. We are interested in robust changes in the Adderley circulation. So the first thing to investigate is always the seasonal cycle changes. In the first row, we have extent and strength in the northern hemisphere, and the second row here we have extent and strength in the southern hemisphere. The collection of sorting experiment in this way is also useful because you have implicitly also an indication of the temperature changes because it is increasing from LGM to RCP85. So the Adderley circulation is expected, as also previous studies said, is expected to expand poleward in both hemispheres, and it is projected to be weaker as the climate warms. Just mid-Holocene has some kind of different behaviors because, of course, it's the most different experiment among our collection. And in fact, the Adderley circulation is shifted poleward than PI control, despite in this experiment, the global mean temperature is less lower than PI control. And in the southern hemisphere, the southern Adderley circulation is also stronger, and this can be related to monsoon dynamics. The Adderley circulation here, we are focusing on in this study, we are focusing only on winter values in both hemispheres, of course. And we are analyzing changes in the stream function between most different experiments, the LGM, mid-Holocene, RCP85, with respect to the pre-industrial condition. As we can see here, the cold and the warm experiment are almost are opposite, in the sense that in the colder climate we have a strengthening of the Adderley circulation in both hemispheres. The tropopause height is lower than with respect to PI control, and also the Adderley circulation is equatorward contracted. The opposite happens in a warmer climate. Mid-Holocene again has very different behaviors from both experiments, suggesting that orbital changes are so much more important. To assess which is the main mechanism that is leading changes in the Adderley circulation with the climate change, we are computing different regression models for near surface potential temperature contrast, static stability, and tropopause height. And since the scaling theory says that all of these predictors are related to Adderley circulation dynamics, we computed also the multiple regression model accounting for 3 predictors. Analyzing scatter plots, in the first row here we have strength, extent and strength in the northern Adderley circulation, The first row has on x-axis meridional temperature contrast, static stability, and tropopause height. We can see that the Adler circulation is expanding poleward with a reduction of meridional temperature contrast, and with the increase of static stability and increase of tropopause height. Here we have reported just values with the tropopause pressure level, so it's different. But for the strength, we have the weakening of the Adler circulation with the reduction of meridional temperature gradient and the increasing of static stability, and again the increase of tropopause height. It's good to notice that if we put out LGM experiment from this regression fit here, we cannot see anymore a very clear relationship with the meridional temperature gradient changes. The same, we did the same for southern Adler circulation, of course, and it's pretty clear that we have an expansion of the southern Adler circulation with the increase of static stability and tropopause height. The problem related to the southern Adler circulation is that mainly we have an increase, and it's pretty robust across this experiment, an increase of the meridional temperature contrast between tropics and extratropics in the southern hemisphere from LGM to RCP85. Now, we cannot see anymore any kind of dependence from the Adler circulation, the southern Adler circulation strength, because mainly data are not very well stratified with the temperature itself. Summarizing previous results about scatter plots, we have a bar plot here with correlations. So we can see that in both hemispheres, for extent and strength, we have the same sign of the changes, while it is not true for meridional temperature gradient change. So the problem is that the Adler circulation in the southern hemisphere, it's expected to be wider, and no, we cannot say anything about changes in the strength, because mainly we have an increase of the meridional temperature gradient. Since static stability and tropopause height are strongly correlated in both hemispheres, northern hemisphere red values and southern hemisphere blue values are strongly correlated with tropical mean temperature, we can say that analyzing the variance explained and only using the tropical temperature as predictors and the variance explained by the combination of three predictors here, we can say very clearly that tropical temperature alone can be used as the only predictor, the best predictor to analyzing future changes in the Adler circulation, since it explains almost the same variance of using three predictors here. So, concluding, the Adler circulation will expand in a warming climate at a rate of 0.35 latitude degrees for each Kelvin of warming for each hemisphere, and it will be weaker only in the northern hemisphere with a rate of 6 per Kelvin. It seems that the main driver for Adler circulation changes are static stability together with tropopause height increase. And the uncertain response of the southern Adler circulation strength, if you remember scatter plot, we cannot see any dependence from those parameters. We can see that it's possibly due to a partially compensating effect between the meridional temperature gradient increase and also the subtropical static stability increase in the southern hemisphere. The tropical temperature can be used as the sole predictor to understand changes in the Adler circulation, and we should think about what is the response of meridional temperature gradient in the southern hemisphere with global warming. So thank you very much for your attention.
Can I ask how these results compare to observations? Because clearly you've only used models here.
This is something that we didn't investigate. But it seems from my previous study that observing the expansion rate and weakening rate, there is a pretty good agreement with what I previously found on reanalysis mainly. So yeah, I think it's something that we can trust.
I would like to show you some first results of our work at MARUM in Bremen as part of the PALMOD project, in which we start to work with coupling ice sheets and climate. And these are some first results of this, together with a big group of people. And I'll be talking about the British-Irish ice sheet and the potential relationship with the AMOC during the LGM. Here are overturning stream functions figures from two models, CZM3 and CZM4 for LGM and pre-industrial. Both are run at relatively high resolution, 1 degree in the atmosphere, that is, and also about 1 degree in the ocean. And I use them sort of as typical models in a discussion whether the LGM ocean circulation, the AMOC, was actually stronger or weaker than the present day. And so you can see that in CZM4 on the right is a typical model that shows a strengthening of the AMOC for the LGM. And on the next slide you will see that there are many models that show this feature. And in fact it shows a 38% increase of the maximum overturning strength. On the other hand, there's CZM3, which shows a weakening of the AMOC by about 28%. And this somehow fits into a general discussion about the LGM overturning stream function, whether it was streaker, what was shallower, weaker, stronger. It's not clear from proxies. As I will also show some proxy SST reconstructions. But first, some model results. You don't have to go into all the numbers. It's just to show that from PMIP2 and PMIP3, different models give different results. So there are some in red that give a weakening of the LGM overturning stream function. And then quite a lot of the models show actually a strengthening of the overturning stream function. And to all this data, I would like to add a new piece of information, namely the existence of the British-Irish ice sheet, to which I will come in the end of the talk. Firstly, the typical pattern you would expect for a weakening or a strengthening of the AMOC is the heat transport. So for CZM3, we see that the heat transport towards the north by the ocean is weakened. So the LGM is below the pre-industrial values throughout the northern hemisphere. In CZM4, it's a little more complex, but overall, the northward heat transport is stronger than for the pre-industrial. And this has clear implications for the ocean heat flux, so the heat exchange between the ocean and the atmosphere in the northern hemisphere, in the North Atlantic. In this figure, positive means that the atmosphere gains heat from the ocean, while bluish colors means that the atmosphere is cooled by the ocean. What you can see is for CZM4, the colors become more reddish in the LGM, which means that the ocean is providing more heat towards the atmosphere. While in CZM3 it's the opposite. The ocean is actually cooling the atmosphere in most of this region. And I'm specifically concentrating on this, the box that you see on there, which I will call the drift region, or you can give it any name, but that's the region I'm concentrating on, mostly because we think that's the part of the ocean that's really relevant for the British-Irish ice sheet, or the region in general. The impact on the sea surface temperatures is also clear. These are the absolute sea surface temperatures for CZM3 and 4 for the LGM. And there's clearly, it's much cooler in CZM3 in this area compared to the other area. Almost by about 10 degrees cooler, in fact. There's many interesting details as well in the ocean circulation given by the arrows, which I do not have time to go into, but similarly for the surface air temperatures, I'm concentrating here on the summer surface air temperatures because we think those are the relevant temperatures. That's the relevant season when you're talking about ice sheets. And similarly to the sea surface temperatures, you see that the area around the British-Irish ice sheet is much cooler in season 3 compared to season 4. Again, about 10 degrees cooler in this area. As a short side note, in this project we are working towards a fully coupled ice sheet climate system, which means we will actually be using absolute temperatures. In most studies so far, people have always used anomalies, but we are using absolute temperatures, so it's also very relevant to look at the biases in the present day climates of these simulations. And what those show is for season 3, it's a little hard to see, but you see a lot of bluish colors here. So these are summer SSTs compared to climatology. And in general, you can say that for the area, season 3 is a little too cold. On the other hand, season 4 is a little too warm. Similarly for the surface air temperatures, but it's probably very hard to see. The signal is muted, but the similar pattern is there. Then I will compare this data with the MARGO data set, so SST reconstructions. The MARGO data, the MARGO SSTs themselves are given in the top plot, the temperatures, and the lower plots, you can see the numbers from season 3 and 4. And already from this, it seems clear that season 3, in this area at least, is a little too cold, and here it's too warm. But as I will show in the next slide, if you take all the MARGO data set together, it's actually not easy to show which simulation is better. Which is given here in the left-hand plot. It's a scatter plot of the reconstructed temperatures versus the simulated temperatures for the same grid cells for the two simulations. And you can see it's not easy to determine, based on SSTs, which model would be best. And so perhaps it's also not easy, based on SSTs, to say which AMOX situation is more in line with SST reconstruction. So a weaker or stronger AMOC, it's difficult to determine from this kind of plot. Then if you remember the small box I had on the maps, the drift region, that's what's given in the right-hand plot. So there you can see that there is a more clear difference between the two models, with season 4 temperatures being too warm and season 3 slightly too cold. I like to say that the bias in season 3 is a little smaller, but they are both biased, it's clear. So what affects, how does this affect the buildup of an ice sheet? So we use these climate simulations in an offline ice sheet modeling exercise with the PISM model, run on 20 degrees, and well, there's many details to these kind of ice sheet simulations, which you can ask afterwards if you like. But in general, what you get is if you use season 3 fields, so that is absolute temperatures and absolute precipitation. This is the Northern Hemisphere LGM ice sheets you get, the equilibrium simulation. And on the other side, you can see the season 4 ice sheets. And there's many interesting features in there, but as the talk suggests, I will focus on the British-Irish ice sheet, which is down here. While on the other plot, so for season 3, it is actually here. For season 4, it's not. As you can see, there is no ice sheet. There is no British-Irish ice sheet. Well, from data, we clearly know, it's maybe not all too easy to see, but in the middle plot, there are all kinds of dates, different methods from a reconstruction, a recent reconstruction. But overall, it's clear there was, in the LGM, there was actually an ice sheet over this area. So the intriguing finding is that somehow our results suggest that if you use season 3, a colder North Atlantic because of a weaker AMOC, you are able to grow an ice sheet over this area. If you use a stronger AMOC, warmer North Atlantic, it's not possible to grow this ice sheet. Now there are all kinds of parameters and knobs in an ice sheet model, but we've done many sensitivity tests, and it turned out not to be possible to grow an ice sheet in under CCM4 boundary conditions without completely messing up the other ice sheets. So it's quite in that sense, a robust result. Which brings me to the conclusions. A reduced northward ocean heat transport associated with a weaker AMOC during the LGM is both consistent with Margo data, so SST reconstructions, but those alone do not really allow you to distinguish between a weaker or a stronger AMOC for the LGM. However, we think that an ice sheet reconstructions provide some additional evidence that point towards a weaker AMOC during the LGM. And then a short note which I referred to is that the sign and magnitude of a present-day model bias becomes really important when you are working with or working towards fully coupled ice sheet climate systems, and they cannot be ignored in this kind of study. Thank you.
If you use CCSM4 and you look at vegetation in Europe and you compare it with the proxy data for from Poland, for example, it's also totally it doesn't match well at all. So it's very clear that CCSM4 actually among the PMET3 models is an outlier in the warmness of the European climate, and you get boreal forest growing right up to the edge of the ice sheet. So it's another piece of evidence along with your British Irish ice sheet that shows that that's probably not super realistic.
Yeah, thank you. I think it's, CCM4 is too warm, and as I showed, CCM3 is a little too cold. But I think combined they somehow show that there is some information about the AMOC to be gained from using this kind of work. But yeah, the European temperatures are clearly connected to the story.
You were concentrating on the British-Irish ice sheet, but what happens for the other? It seems that you are building an ice sheet over Siberia as well. Yeah, that's another interesting story that we got out of the simulations. Yeah, many, I would say most coupled simulations, coupled ice sheet climate models give you an ice sheet over Siberia. Yeah. So in that sense, there's an issue there as well. One of the models does, and the other one does not.
Earl kindly asked me to, unfortunately he couldn't come to the meeting, but he kindly asked me to give his presentation for him, which he actually prepared for me. So I'm going to do my best, and I think I'm just going to give you a bit of Earl's perspective on anthromes and anthroecology, and I'll give you a bit of my perspective on anthromes and anthroecology as well. Okay, so Earl is very much Mr. Anthropocene, if we want, and so he's come up with laws of the Anthropocene. So we are now living in this new era, and I don't actually want to get so much into the discussion about when it started, but we are definitely in it. So we are in the Anthropocene now, and it's going to continue for the foreseeable future, as he wrote. And so there's this kind of changes in human society over the next decades, centuries to millennia will have both sort of short-term dynamics and long-term trends associated with them, what Earl terms as sort of human weather and climate. So there'll be events, there'll be catastrophes, there will be societal changes like wars or things that are really happening on a short-term basis that affect the planet. Then we have some kind of very long-term trends, for example, related to the evolution of technologies that will persist for centuries to millennia. Okay, we know not to wade too deeply into the when did the Anthropocene debate begin debate myself, but we know that humans have transformed the Earth's land surface for millennia. And those of you who know me know that I say this all the time. We just to remind you, things like the megafauna extinction are probably even quite closely related to anthropogenic activity, and certainly by the time we get into the early Holocene, parts of the world are being fairly extensively altered by human activity. So we don't want to think about the so-called wild biosphere anymore. There's no such thing as wild biosphere. There's no such thing as potential natural vegetation except in your head. Okay, so this is sort of a nice picture, but really the world we live in is something that looks more like this. And it was Earl who originally came up with the idea for so-called anthromes. The anthropogenic biomes is simply a way of classifying and depicting the sort of state of the Earth's land surface and the Earth's land surface system in a classification method that's easy to understand, I would say, and anybody can sort of digest this fairly quickly, and you can also realize that the potential natural world just really doesn't exist. So then there is this kind of question about how did the biosphere become anthropogenic, and actually I wouldn't labor these 3 slides because actually they're all wrong. But really what you need to look at is this bottom picture here, which is sort of something that I've been working on. So it really shows that the imprint of human influence on the Earth's land surface is, again, as I said now 3 times already, something that's gone on for many millennia. Okay, so there is this idea of an Anthropocene transition. When did it happen? Where did it happen? And what do different scenarios say? I would say that actually the science is moving on from KK10 and Hyde, and so we don't need to belabor the point. Suffice it to say that, once again, the Earth's land surface has been substantially transformed through human action. So anthromes by themselves are sort of, as I said, it's a valuable way of making a kind of easy to understand and quickly grasped classification or quantification, if you want, of the way that humans have transformed the Earth. And Earl has put a huge amount of work into sort of developing materials for the public to try to help them understand the anthromes concept and to understand this idea of human influence on the planet. And that led to, for example, the inclusion of one of his maps in the National Geographic Atlas and lots of other kind of media type exposure. So there's an interesting thing though when we think about the way ecology is done today. Most ecological research is actually done in areas that are somehow not in those used landscapes, in those used anthromes, but they're actually in sort of protected areas where people sort of think that there's potential natural vegetation. And this is actually, in a way, kind of problematic because we actually need to be studying the landscapes we live in, not those just little jewel boxes that we set aside as kind of nature preserves and that sort of thing. So that's something that we certainly need to keep in mind. So this is all leading us to a new sort of paradigm, a new idea called anthroecology, which Earl is really promoting. He has written an entire long rationale of this in a paper that's come out in Ecological Monographs recently. And the basic idea he starts out with is, why do humans transform the ecology of the planet? So what is it that drives them to do that? And that's has these 3 sort of major components: the sociocultural niche construction, evolution, anthroecological change. And just to give you an idea of what he means by sociocultural niche construction, he's sort of showing these sort of different phases of niche construction related to changes in our culture, cultural or intellectual heritage or material culture, and the way in which we modify ecology, and contrast the sort of end of this genetic inheritance here. Now these lead then to changes in the way that we use energy. Okay, so we have sort of a long part of human history where we use our only source of energy was biomass, and we sort of transform to fossil and various types of abiotic forms of energy, and also how we transform ecosystems. Now, I think it's when I first saw this slide, I said, yeah, these are kind of pretty pictures, but it's completely wrong because you're going to give the audience here the impression that this is a kind of linear process, and it's certainly not a linear process. You know, not all societies go through all of these steps. Some go forward and they regress, they go back, they go up, they go down. So really, then he put in this kind of tree of life figure to sort of display that, which was not really what I had in mind when I said. Put something in to explain it, but suffice to say, the process of this kind of niche construction is something that would look much more random in real life, or was much more sort of random and based. There is a certain path dependency. Societies start to go down one direction, like increase in biomass or the use of fossil energy, and as we know very well right now in the present day world, if we want to get off of fossil energy, it's quite a challenge. Okay, so this kind of niche construction can be displayed in the form of these sort of so-called anthrosequences. The idea is that as people change their subsistence livelihood, it changes their influence on the landscape in different ways over time. And these make very, very pretty colored pictures, but they also sort of, I actually think that it does play into something that I've been working on, and Earl and I have collaborated on over the last few years, the idea that there's a certain amount of this transition in these anthrosequences that's not predictable, okay? So we can't, on the basis of climate or some kind of other properties of the physical environment, determine when this transition takes place. But it's very important because when the transition from one sort of societal or subsistence livelihood happens, the whole way in which humans affect a landscape changes really drastically. So there is actually quite a large influence in terms of land use, even in this hunter-gatherer society, but it's just a very different one than the one that occurs when you're agrarian or industrial. So I think that, this is one of the reasons why, just to give my own opinion in here, this is one of the reasons why pages and those of us involved in, particularly in paleoecological research, need to reach out and work much more closely with archaeologists, ethnographers, sociologists, and so on, to try to understand really how and when these kind of major transitions occurred. So you can also sort of plot these then out in terms of anthromes and show how they would change on a map, but you can also show how they would affect various different kinds of things like ecosystem services, biodiversity, and so on, and even what Earl likes to call development of novel ecosystems. So the key point here is that in each of these transitions, humans are having a big influence on the environment. It's not something that only comes with the industrial world. It's something that evolved actually thousands of years before, but it was just in a different way, had a different expression, and that expression affected all different kinds of aspects of the Earth system. And finally, as I said already, we can't necessarily predict that on the basis of any kind of physical environment. Here's just a few other characteristics that change. So combustion, fire, NPP, and so on. Okay, and so again, to sort of just again to put this on a timeline to see how did these change. Well, this is obviously totally oversimplified. I would never put this in my own talk, but now again, I mean, it just kind of shows. Okay, this idea that there are these sort of phases, and those obviously don't occur linearly. And I think he's trying to sort of show that by saying, okay, hunter-gatherers sort of persist even right up to the industrial era, but they just become less and less, as well with horticulturists and so on. But the real trajectory of human history was much more messy. There was a lot more. There would have been a lot more sort of variability. It would look like one of those kind of spaghetti plots or squiggly lines that you see in all the other presentations given at this conference. So this is really kind of just to give you an idea of a very simple conceptual idea of how it might have changed over time, but I would say that it's a kind of a drastic oversimplification. So finally, I think Earl's major point that he wanted to make is that human systems are part of the Earth system. We have to take that into account in not only when we think about the future, but also when we think about the past. And Pages is certainly moving more and more in that direction, which is something that's really welcome by many of us. And so just a kind of plea to everyone to think about, how we can incorporate this kind of human system, human influence, when we think about changes in the past. And I'll leave it with that. Thank you.
How much the reconstruction for the anthromes match some other reconstruction of the landscape, like based on pollen, I mean in time?
Yeah, that's a very good question. I mean, so if we take these kind of historical or prehistoric reconstructions of past anthromes and we compare those to independent reconstructions of land cover based on, say, pollen data. That's the paper that I promised to Marie-José for 5 years now, which I would promise I will submit. It depends a lot on the scenario, and so yeah, the scenarios of past. It seems like, for example, the Hyde-based anthromes data set that many people use really predicts much too little human influence on the Earth system in prehistoric and pre-industrial time, and that the KK10-based anthrome reconstruction is better, but I would be the first one to say it's still not good enough.
Is there any way that you can incorporate not just the environmental variability of the pollen and into some of these conceptual models, but also what the role the human population size itself is playing? So, for example, how does that feedback onto the fact that, for example, you can have different cultural periods, right? So you're going through hunter-gatherer phase, and the hunter-gatherer phase, you may not have a lot going on in population, but once it gets into the agricultural phase, it explodes. So how does that feed back on these conceptions, on these conceptual ideas that you have?
Yeah, that's a good point. And so actually, it's very interesting. In all of the scenarios that we have, the sort of past land use that people are using today, like Hyde or like KK10, they are driven by population data, which you put into them, which is sort of ignorant of these kind of major transformations. So these kind of subsistence transformations. The new generation of land use models that we're working on right now will take it from the other way around, where what you prescribe is the land use system. And you should listen to Andrea Kay's talk tomorrow, where she's going to explain to you how this actually is done, and they will have population as an output of the model. We won't need to estimate it effectively anymore, and then we will be able to really capture that feedback process much more clearly.
For those of you who know me, I'm a lake guy, but I live now in Texas for long enough that I've had to do something else. You know, there's no natural lakes in Texas. It's crazy, right? So we had to find something else to do. So I'm actually, let me see if I can, sorry. I don't know how to use pointer. It's okay. This is gonna be from cave sediments. So yeah, the first thing I say is caves, and people are like, oh, speleothem. No, this is the stuff that the speleothem people walk on. But actually, and the first thing you might think when you see this is, well, that's probably going to be a horrible record. It will have a terrible chronology. And look how bad that is. Okay, I have no idea what's going on. Am I hitting the wrong button? Okay, there's a chronology, right? So this chronology, sorry about that. So this chronology is based on 45 AMS dates on bone collagen. So extracted the collagen and actually produces, that's like a late chronology. It looks pretty decent. So just to start off, right, I just wanted to get rid of the cave skepticism. So the other part of this, right, is that this record is from Texas. And some of you may be like, that's not the Southwest. But I think it's actually kind of a cool place to look, especially at vegetation change, because in this area, right, we have this really remarkable vegetation gradient between East Texas has like humidity of like 90% and pine forests, right? Where I live is sort of in the middle, where that kind of near the red dot there. That's our study site. And if you go all the way to the far west side, right, you have desert grasslands. And so in between, you go from prairie, and then this sort of our site is located in this transitional post-oak savanna, right? So it's a really strong vegetation gradient, and so it's kind of interesting to think about, how stable is this gradient and how does climate influence it? All right, and there's some reason to think about this. This is one of the reasons we started thinking about this. This is a picture of these really large old live oaks from Zilker Park in Austin from September 2011. Everybody from the U.S. certainly knows about this, that 2011 was this really bad drought, and the Forest Service estimates that in Texas, as much as 300 million trees died. And they weren't like little trees in my backyard. You know, some of these were, you know, these live oaks and things like this. And you know, they didn't die directly because of the drought. They died because of, you know, stress, and then they got disease. But still, you know, this suggests that, you know, you can have really dramatic changes in vegetation associated with climate. All right, and that's because these vegetation gradients are basically directly driven by a massive precipitation gradient, right? And this is just showing the seasonal climatology here. The red dot, again, is our study area. And what you can see is you get, you know, in the winter, DJF up on the left, you get this strong westerly flow. You get most of your precipitation to the east. And as you move into the spring, right, the winds switch, and you get these meridional winds that are coming up from the Gulf of Mexico. They're advecting moisture, right, and that moisture, as it comes across the continent, is generating convection. You're getting a lot of rainfall. So you're basically expanding that precipitation zone westward, right, and that's allowing these transitional zones to develop where they are. And you know, what I want to point out is that you do get rainfall in the winter, but you know, as a proportion of the annual total, right, it's pretty low. Most of your rainfall occurs in the spring and the fall. That's associated with this meridional flow. In the middle of the summer, you actually get a reduction in rainfall not because those winds slow down, but because you develop basically the Nash migrates over, and the high pressure essentially inhibits convection. All right. So, and you know, one of the most important climatological features in this area is the low-level jet. The low-level jet is a geostropic wind that's generated basically by the pressure gradient between a low that develops by heating east of the Rockies and the subtropical high, right? And it's really important for generating convective precipitation. You get all these big mesoscale convective systems. So if you guys have watched the news, you see these big floods in the spring that are happening in the Midwest. This is what causes it. You get these massive convective systems that generate a lot of rainfall. And that's just basically where we're getting most of our rainfall. And the important part for us is that it's primarily convective. That's going to be important for isotopes. All right, so our proxies we're going to use the carbon isotope composition of, I'm just doing bulk TU. So we actually looked at leaf waxes as well on a couple samples, and the data looks very similar, so this is cheaper and easier, so we did this. And, you know, we would do, for Will and those guys, you know, we would do pollen, but the pollen is really degraded, so we're going to go with our carbon isotopes. And, you know, one of the nice things is that, you know, our region, this vegetation gradient, is also a very strong gradient in the proportion of C3 and C4 plants. So we're going to use our carbon isotope values basically to just reconstruct that. All right. Now, when we talk about isotopes outside the tropics, right, there's been lots of tropical isotope studies people talk about here. It gets a little more complicated when we move into the, you know, into other areas. But fortunately in this area, I think we have I can argue that we have a strong amount effect. And so I have a student, Shijun Sun, who has been working on this, and we've been basically measuring individual rainfall events for a couple years. These are high split trajectories for those events. And what I want to get across here, right, is that most of the big rainfall events are convective. They're coming up from the Gulf. They're associated with a low-level jet. You do get winter rainfall events, but they're small, right? And if we look at the isotopic composition of these rainfall events, there's a strong correlation between amount and the delta 18 or delta D of that rain if it's primarily convective. So the less convective it is, the relationship starts to fall apart. Fortunately, non-convective rainfall is a small proportion of the total rainfall, right? And actually, when we get large non-convective rainfall events, they actually fall almost on the same convection line, right? So we're going to make the argument here that we can use delta D as a recorder, as an indicator of precipitation amount. And if anyone wants to ask me more about that, I can talk to you about it later. Okay, so this is our carbon isotope record. So it's about a 19,000-year-long record. And what you can see is that during the why can't I get this to work? Oh well. Okay, so during the early part of the record, right, we're dominated by C4 summer grasses, and then we have this big pulse of C3 plants. It's like a 20 to 30% increase in C3 plants during the deglacial. It goes kind of back down during the younger dryas. The early Holocene looks like it's predominantly grasses again, and then we get this huge increase in C3 plants during the late Holocene. So we have like a really dynamic vegetation. So this is changing a lot. It's clearly responding to something. And even superimposed, you get these pretty large millennial scale variations. Other thing to notice is that the modern vegetation regime is basically the greatest proportion of C3 plants that have existed there for 20,000 years. Right? So it's not like this system has been stable and it's basically, today is actually somewhat of a unique situation. All right, let's look at our hydrogen isotope record. And so up is wet, dry is down. And you can see that actually shows a lot of the same features. You see the big hump that occurs during the Bowling-Alderod there. You see dry conditions in the Holocene, and you see this sort of late to mid to late Holocene, a sort of increase in precipitation. And this is from the C27N alkane. The other ones look pretty similar. So one of the problems, right, is that if you are a biomarker person, those are large changes in vegetation, and there are large differences in fractionation that are associated with different vegetation, right? So one of the problems could be these delta D variations could be an artifact of those differences in fractionation if we're not doing a good job of correcting for them, right? So we also looked at, and this is going to blow your minds, we also looked at percent titanium in the same record, right? And I mean, you can't ask for better than that, right? So I just couldn't believe it when I plotted this up. So right, so this the idea is that percent titanium is essentially the percentage of titanium diluted by calcium in this cave, and it's basically getting washed into the cave, right? And so when we have greater, precipitation, then we're going to wash more titanium, and we get greater concentrations. And it seems to reflect most of those main features. And so this gives us some confidence that we actually have delta D is really actually giving us some sort of amount effect record. All right, so we can compare the two records here, and you can see, right, that, from 14,000, 15,000 years ago to present, the carbon and the hydrogen look virtually identical, right? So clearly precipitation is the dominant control on vegetation changes that we're getting. One thing I want to notice is look at the difference prior to the Bowling-Alderod, sort of the glacial type of sort of period. Right? We have very, very high abundance of C4 plants, but we have relatively moderate levels of precipitation. So it's relatively wet, but the vegetation is this drought-tolerant grasses. And how do you get that? Right? And so I think that there's two possible explanations for that. One would be, right, the CO2 explanation. That is, lower CO2 favors C4 grasses, and so therefore you can't bring in the C3 plants. The other one, I think, that is something we're working on now, we're going to generate a fire record, is that perhaps the C4 grasslands are sustained by fires. Often in these savanna-type environments, when you have large proportion of C4 plants, you get really frequent fires, and those can basically prevent C3 plants from getting recruited into the landscape. So, okay. So now I wanted to look at why we get these other features. I worked with Mr. Page's Nick McKay, who's here somewhere, and we were looking at some of the trace simulations to try and figure out 2 minutes. Oh boy. The controls on precipitation. And so what I would say is, right, these don't look all that similar, but they do have some similar features, right? One is that the trace record shows wetter conditions during the sort of earlier part of the record. And that's primarily controlled by winter precipitation, right? And so this is basically storm tracks getting deflected by the jet southward. And I think what we can contribute to this is that this is actually the easternmost record that shows this. So this tells us that those storm tracks are pushing precipitation during the glacial all the way to central Texas, keeping that entire region wet. Now the other thing to look at if you look at seasonal is to look at spring, right? That's when our low-level jet is happening. And we get this really interesting peak of spring rainfall that occurs, relatively close in timing to our big peak in our delta D record. And we looked at this in a little more detail, and this is basically driven by spring insolation, which drives essentially meridional winds, right? So essentially this is an intensification of the low-level jet as it's simulated in the model, which is not that great. So there's obviously some differences here, and the main one, right, is that the model basically shows the low-level jet intensification occurring out into the Younger Dryas and through the Younger Dryas, where we don't see that in our proxy record. And that could be due to some problem with the model, we're not sure. So we kind of looked around to see what other records there were that could help us, and I found several, there's not very many, that are in this area that the model suggested should show this big increase in precipitation. And they actually, a number of records show that, but they all show the precipitation declining before the Younger Dryas. So there's clearly some difference in the way the proxy records are recording this and the way the model is simulating it. And that could be a model problem. It could be something that's, or it could be simply that it's just a totally different mechanism. So this is something we're obviously working on. Okay. There's one last thing I just want to talk about because I know I'm over, but this really interesting feature in the Holocene. And so there's two ways to look at this, right? There's that precipitation increased a lot, but also that precipitation was just simply drier during the Holocene. And the fact that precipitation was lower in the early Holocene is not surprising. All the models show it. This is just a really nice nested model that Bakker did in 2006. It's basically, essentially what's happening is it's the inverse of what we see during that spring rainfall peak during the Bowling-Allerrad. You're getting a weakening of the level jet and less advection of moisture into the continent. The problem is that most of these simulations show big changes for the summer when we don't actually get that much rainfall, and it's not clear that they can produce the magnitude of the rainfall changes we actually see in the late Holocene in our record. So there is one other possibility, and that is that it could be the tropical Pacific. We know there's a number of records suggesting, Jess Conroy's here, right, her UNCO record, right, and these suggest that there's an increase in the intensity or the frequency of El Nino events. These have a strong impact on spring rainfall in Texas, and spring rainfall is actually really important for growing vegetation, right? And so it's possible, these do actually look quite similar, and it's possible that that's the control. All right, so my last slide, good and bad, the ugly of this talk, and you guys can, since I'm over, I'll just flip them here, and you can ask me a question. But by the way, right? This was this movie was filmed in Spain, right? Do you guys know that? So.
If you assume that you have different type of rainfall in the glacial part, and you would correct for that, what would happen to your deuterium record? Which way would it go?
So I think the question is. So I'm assuming from the model, right, that our rainfall is primarily winter, which is actually stratiform, right? That should be more negative. So it could actually, without increasing the total amount of rainfall very much, you could actually produce a more negative signal. The problem is we have the titanium record, which also suggests that precipitation was quite a bit higher. So I don't think that's that's not a satisfying explanation.
I understand. I'm the last talk. I'm going to make it really brief. I'm going to wrap up sort of combining almost everything that you've seen in this session. What we're going to do is we're going to take a global perspective on glacial to interglacial climate variability. This is work that I've been doing when I was in the Young Investigator group of Thomas Lepple and with my co-authors Thomas Munch and Sining Ho, who were also in this group at that time. It's 3 years since we started this work, so we've sort of moved on, which means I'm now at the British Antarctic Survey and Lingers in Bergen, but this is Science Life. So why look at climate variability and how it would change from the glacial to the Holocene? One motivation is our mean climate is shifting, and it's going to shift quite a lot towards warmer temperatures, and it's really unclear how this affects climate or temperature variability. What can we learn from the paleoclimate record? So what is the state effect on climate variability? And then what I'm going to argue is that we can really look at the LGM to Holocene transition, as it's a roughly 2.6 or 2 to 5 degrees Kelvin temperature change from the LGM to the Holocene. So, most of what we know about the last 25,000 years of the glacial to Holocene climate variability change is really focused on Greenland and on the iconic North Grip or any other North Greenland ice core record derived from oxygen isotopes. And we have 40,000 years before present here, going towards the present day through the glacial. This is smoother, but you see this huge variability DO events, which there was a dedicated session about. But even in the last glacial maximum outlined here, there's quite a lot of variability if you compare this to the Holocene, our current warm period here. And there have been papers suggesting that this stability led to cultural evolution, migration. There was impact on whatever brain evolution. And what we're going to do now is to basically look at this from a global perspective, not just looking at the North Grip ice core. If we do this, we want to look at more proxy records. So we still have sparse data in time and space. They're irregular, uncertain. We don't really know how they relate to temperature. The way we're going to do it is we're going to use the variance ratio, so the ratio between the variance in the glacial and the Holocene, so we can more easily intercompare different proxies for temperature. We're going to use the power spectrum to be able to filter out differences in resolution. And we are recalibrating proxies which have a global calibration in order to make them more comparable. We assume a signal-to-noise ratio. I'm happy to talk about that later if necessary or if somebody is interested. So we are using a 1.5 signal-to-noise ratio for Greenland because these records are quite well replicated, and everywhere else we're using a signal-to-noise ratio of 1. We do also check the sensitivity on calibration uncertainty and sampling using power laws. So this is our data compilation. We have North Grip and other Greenland ice core records for the Holocene and the LGM. Everything in red spans both periods. Everything in green only is for the Holocene, and the LGM is in pink. You see here the LGM to Holocene transition, and the bandpass filtered temperatures at the bottom show a large variability here, whereas we have very little variability in the Holocene. If we go to any different record really in this compilation, we don't see this large change in variability. In total, we have 27 records that cover both periods, with at least 4,000 years and a minimum resolution of 225 years. So we are able to say something about 500-year to 2,000-year timescale variability. If now I didn't take only those records that cover both periods, and I took everything that covers the LGM and everything that covers the Holocene, and I get the variability in temperature from each of those, and I divide the variability in the LGM by the variability in the Holocene. This is the probability distribution for the global temperature variability change that I'm getting. It's really huge. This is a logarithmic axis, so anything between a variability change by a factor of 20 and 0.5 to 0.1. But the main point is it peaks at around 5. If now I go to only those records which cover both periods, where we really can assume that the proxy relationship is a bit more stable, we still peak at round about a variance change of 5. Now, the important part is this does not include the Greenland records because they actually plot at the other end of the scale. So, roughly, we can say that glacial temperature variability is around about 5 times higher at the glacial maximum than Holocene variability, and the Greenland changes are a lot higher. Now, what could give rise to this change? Here we could involve the AMOC, and forcing and feedbacks could possibly give nonlinear effects. Or we can say we could have a higher stochastic forcing due to a higher temperature gradient in the glacial because it was just in general colder. The AMOC does not really fit the bill because pretty much all the AMOC manipulation experiments that we've seen, and I could list more here, they do not put the maximum response over Greenland, but rather the more broader region. If we look at our results in a bit more detail, we can see that we see a minimum change in variability in the tropics, larger changes in the mid-latitudes. Greenland is really high, whereas in Antarctica we see an east-west pattern. In the background you have the temperature gradient. That really fits quite nicely. So if we put this over the latitudes and we look at zonal means of the variability change, we have small changes in Antarctica and in the tropics, larger changes in the mid-latitudes, and really high changes in Greenland. This is the temperature change derived from Annan and Hargreaves. This is the change in the temperature gradient that could have driven this change. this is if I sample the temperature gradient at the proxy positions, and these are the individual estimates for the variability change from each proxy, where I have both the LGM and the Holocene present. And the amazing thing to me is, when we look at this, it really fits quite well. So where we have no change in the temperature gradient, we roughly have no change in the variability. And this translates to an actual significant correlation for proxy records, which is, again, something I was quite happy about, but surprised as well. So to conclude, we've taken a more global view on the glacial to Holocene variability change. We find that the LGM is around about 3 to 8 times more variable than in the Holocene. We'd say that Greenland is definitely higher than anywhere else. And everywhere else, the variability change fits quite well with the change in the overall temperature gradient, which could tell us something about the mechanisms that underlie this. However, there are still open questions because we don't know if this Greenland signature is related to temperature or to proxy-mediated changes via sea ice and seasonality. So in order to be able to say what really the role of Greenland is in this, we would really need other temperature records for both time periods to say something. Thank you.